enlisted to give this talk, which I'm happy to actually. But there's not much of climate or networks in my talk. We'll see how it goes, So yeah, so I have planned 2 talks, but depending on how hungry we get, we'll have to probably terminate talk 1. I mean, whenever the time runs out. But talk 2, I sort of will be sort of more interesting for the research part, where we talk about neurochaos learning. So this talk, I just wanted to. I thought anyway, I don't need to motivate chaos, because all of you know that chaos is very much part of pretty much any nonlinear system. But I thought I'll motivate you as to why I want to study one dimensions, And the claim is that's all that you need. You don't need more than one dimension. I mean, yeah, we'll see why that's the case. A couple of reasons. One is topologically, I could not go below 1, right? I mean, 0 is topologically I have to go 0, which I can't. So topologically, I have to do only one dimension. That's one reason. Second reason is you can spend lifetimes, eternity studying just one-dimensional chaos. Amazing patterns, amazing open problems are there. So I never graduated beyond one dimensions for that reason. And last but not the least, the reason I want to do one dimension is because, I mean, my knowledge is limited. I know a bit of this, and this is actually fun. So I thought, let me just spend time talking about it. So, yeah, but I need to show something here. So what I thought I will do is, it's always good to, sorry. Yeah. I mean, it's good to sort of simulate what Lorentz encountered in 1960s, I guess, right? So I thought it's good to do this, and you can go and do it in your home as well. So what I'll do is I'll just open an Excel sheet. Hold on. And you can just try this very simple thing, just to sort of see what kind of problems one may encounter. Okay, so what I'll do is I'll just start with the number 0.2. Is it visible to the people there? The back, yeah, okay. And the next line, I'm just going to take this 0.2, multiply by 16, and subtract 3. Not shared, huh? Oh, sorry. Okay, please do that. Yeah, you can share the whole screen. So I'll just write it here in the meanwhile, So what I'm doing is the following. Sorry, let's say x naught. So what I'm going to, so what I plan to do is, I've just taken 0.2, and then I've taken the previous number, which is 0.2 in this case, into 16 minus 3. What will I get? I'll get 0.2, right? Yeah. So now let me just drag this. I want to drag this. So the question to all of you is, what will happen if I keep dragging this? Do you expect anything funny going to happen? It's just a linear equation, right? I'm just doing x naught in 16 minus 3. It's simple linear equation. So nothing should happen, right? Apparently. But let's see that's the case, Interesting, right? It explodes. I mean, you can keep dragging it and it becomes more than the number of atoms in the universe and all that stuff, But let's do something more now. Let's do 0.25. Okay, and let me take 0.25 into 5 minus 1. So what I'm just doing I'll just write it here so that you can keep both of these guys. And I'm doing y1 is, again, a linear equation, right? What do you think I should get? Again, 0.25, right? So that's fine. Now the question is, let me drag it. And this is where you can play a gambling game, actually. The gambling game is, would you bet your money when I drag it next, will it explode or not explode? So how many of you want to play this game, It's not going to explode. I mean, it's unfair that you are participating in this in this game, How many of you think it will explode or will not explode? The question is why, right? I mean, so, okay, I'm going to drag it, and as Professor Ram rightly said, nothing is going to happen. So just keep this in mind. We'll come back to this, And do you know what's happening here? Again, I don't want the PhDs here to participate. I mean, do you know what's happening here? This is actually prototypical chaos, right? But look at it, right? Both are linear equations, right? I mean, does it make any sense? I'm doing an iteration. So what the hell is happening, right? Just think about it. We'll come back to this in the end, Why we have quote unquote chaos in one and not chaos in the other, right? So let's continue with the presentation. So, okay. So the point is that, as Manish already said, I mean, you don't need any introduction to Lorentz. But what is important to understand is that the Newtonian idea of the world, right? That, and this is what Laplace and all these people thought, right? That give me all the initial conditions of all the particles, and I can predict the infinite future. That's the, that's the ultimate prediction engine that you can build, But you don't need quantum mechanics to have problems, The argument is that, the famous debate between Einstein and Bohr, right? Does God play dice? But the point is, God does not need to play dice, You just need nonlinearity and you need finite precision, right? And you have this problem. So that's the important thing to understand, that just classically you can't predict, right? Classical systems because of chaos. Now, so let's get into the hardcore of it. I want to sort of talk a little bit about 1D maps and symbolic dynamics. Now, I was looking at what's a good prototype to understand chaos. I mean, you have all these examples, right? I'm pretty sure that many of you have taken courses in nonlinear dynamics, and pretty much all these names are familiar to you, right? Logistic map, circle map, tent map, Ricker map, all these kinds of maps, right? And pretty much you're shown these kind of examples, right? You're shown this kind of a cobweb plot wherein, you're shown that as you vary a parameter, things become messy, right? You can see that things become very unpredictable. But what is chaos really, And you can ask this question, and different people will have different answers. So if you are an artist or if you love art, right, you can spend hours on YouTube looking at Mandelbrot sets and looking at all these kind of plots, It's nice, right? Chaos can produce all these visually beautiful things. But if you're not an art lover, I mean, if you're an art lover and you're more than that, you are a physicist or a biologist or most scientists, they'll be happy with these kind of diagrams, right? They're happy with these diagrams, and maybe they'll say, okay, we need something more, maybe the Lyapunov exponent, right? I mean, we'll just say that Lyapunov exponent is positive, it's chaos, so blah, 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 and people are happy, and that's it. But mathematicians are not happy with this, and they say, okay, this is fine, but my question to you is, I mean, do you really see all infinite periods? I mean, the point is, you can't be so gullible, right? Like, how do you believe, okay, somebody is saying Lyapunov exponent is positive, you have all kinds of periods, you have non-periodic orbits. But the argument is it really the case? Like, can you really see chaos, And this is where the mathematicians will come and say, no, we need to prove stuff. We're going to prove theorems, And you can look up this paper. It's not easy to read these proofs, I mean, I tried. It's very, very hard, right? I mean, you can eventually understand it, but York and Lee and York theorem. And of course, the word chaos was coined here, but it was predated by the Ukrainian mathematician Sharkovsky, right? And all of you are familiar with the Sharkovsky ordering of natural numbers. What it says is that you have a continuous map, you have a bounded continuous map, you have period 3, then you have this ordering, like period 3 implies period 5, implies period 7, implies period 9. The entire natural numbers are reordered now. Like if you have anything which is, like let's say you have period 11, it's not the case that you need to have the earlier ones, but you'll definitely have the after ones. So the entire natural numbers are now reordered, So it's an amazing theorem. Again, very, very difficult to understand this proof. So if you are slightly more mathematically challenged like myself, this is a great paper to read actually. It says how to get these proofs using just the intermediate value theorem. I hope you all know what the intermediate value theorem is. It's a very simple theorem. It says that you have a function which goes from, let's say, you have a function which, this is a 0, let's say. You have a function which goes like this, whatever. It goes from a negative value to a positive value. And if it's continuous, then it has to cross 0, right? I mean, that's the intermediate value, right? The intermediate value theorem, and you have various versions of this. Now, this paper talks about a proof of all this, I mean, it's a very, it doesn't use anything more than this. If you know a bit of analysis, you can understand this paper. But then I thought, but even this is too much, right? I mean, even to read this paper, you can eventually understand it, but it takes a lot of effort, So my question was, no, this is not good enough, I want something where everybody can understand chaos. And I'm emphasizing the word all here, Obviously, the question is which books to look for, where do we have this material? And surprisingly, you'll be surprised to know that the answer is, any guesses? Anybody wants to take a guess? Everybody can understand chaos, But you need to have the right book. And it's a book which all of you have actually studied. Yeah? Somebody had said something? No. I'm talking about 9th standard textbook, You go to NCERT mathematics book. And I know it's you're laughing at it now, but I'm going to prove it to you that NCERT textbook has all that you need for chaos. They're not using the word chaos. Maybe the people who wrote the book do not know that they're dealing with chaos, but everything is out there, And I'm going to show you how, So let's look at it, right? Let's look at it. So look at this algorithm here. So take a number between 0 to 1, okay? Multiply by 10 and take the integer part of it. Okay, subtract that from 10x and keep repeating this. Okay, it's a very simple procedure, right? It's a very simple procedure. This, so for example, let's say that I start with 1 by 7. I start with 1 by 7. I multiply by 10. I get 10 by 7. I take the integer part of it. That's 1, right? That's in red here. Now I replace my original 1 by 7 with 10 by 7 minus 1. That will be 3 by 7, right? Then I do the same thing. I multiply output. I take 3 by 7. I multiply by 10. I get 30 by 7. I take the integer part of that. I get 4. Now subtract 4 from 30 by 7. I get 2 by 7. You can keep doing this, right? You keep doing this and you get this. 1 by 7 goes to 3 by 7, goes to 2 by 7, 6 by 7, 4 by 7, 5 by 7, and comes back to 1 by 7. What are we doing here? What has this got to do with NCERT 9th standard textbook, right? So are you able to identify what's happening here? What is this algorithm? What is this 142857? You all know it. I mean, you all do it. You all done it, right? This is nothing but long division, right? This is long division. And the point I'm trying to make is this has everything that you want of chaos. Everything about chaos is there here. We'll explore why, you know, right? You're able to see this, right? 1 by 7. It's long division. I'm just doing long division, right? I'm finding the decimal expansion of 1 by 7. What are the decimal bits of decimal digits of 1 by 7? And this has everything that you want for chaos, you know. And this is just taken from page number 9. If you want to go and look up the book, this 1 by 7 is here, okay? Now, what they don't tell you is that this is the decimal map. This algorithm that I told you is called a decimal map for obvious reasons. Why is it called a decimal map? Because when you iterate any integer, any real number between 0 to 1 on this map, you can extract the decimal expansion of that map. And it looks like this. It's 10x minus integer part of 10x. It's a bounded, nice map. It's mapping 0, 1 to 0, 1. It has these 10 piecewise linear, segments here. And this is a decimal map. And this is everything that you need for chaos. How do we know that? And these are the symbols. We're talking about symbolic dynamics, right? There are 10 intervals, right? 0 to 0.1, 0.1 to 0.2 to 0.3, like that, right? The 10 symbols. You could have used A, B, C, D, E also. You don't have to use 0, 1, 2, 3, 4. If you use 0, 1, 2, 3, 4, you get the decimal expansion. We'll see how it does that, you know. Okay, so now the notations, going back to chaos, right? What do you learn in chaos? You have an initial value, you have a trajectory, right? The initial value is 1 by 7 in this case. You have a trajectory. It could be periodic or non-periodic, right? It can be both, either of them. And what is this 142857? You recall what I did then? I was outputting numbers at every iteration. That's basically telling you which interval you lie in. You remember the 10 intervals, right? 10 intervals with 10 symbols. So the argument we're making is I don't really care about what the actual value is going to be. I'm just interested in which interval I'm going to fall in every iteration. I just record that and display that. That is 142857, right? That's a symbolic sequence. And this is exactly what's happening at every iteration, right? That 1 by 7 is getting mapped to this guy, to this guy, to this guy. But what is this one? This is nothing but it's a shift of this. Are you able to see this? You shift it left, get rid of this 1, you know. You get 428571. You shift this again left, you get 285714. It's actually a shift map. The decimal map is a shift map, you know. It's just shifting digits to the left and extinguishing all which is greater than 1, you know. That's what it's doing, right? Because it's going to be important for us later. It's a shift map, okay? Now we'll do more things with this. So I'm going to just show you what happens, right? So 1 by 7, you start from this interval, right? You hop on to this interval here because 4, 1, 2, 8, 5, 7, whatever, right? Then you go from there to there, from there to there, from there, and then, yeah, you keep doing that. This period 6, obviously now you can see what is going to happen, right? That this is a purely periodic orbit. So in chaos, what do you have? You have periodic orbits or periodic trajectories. You have eventually periodic orbits. It's not periodic to begin with, but they become periodic. That's example is given here, 0.1234. You see this example here, right? Take the decimal number 1234 with this bar is fine, right? Bar means it's repeating, right? What happens in the first iteration? It's a shift map. 1 goes away, 2, 3, 4, and then 2 goes away, 3, 4. Then you have 3, 4, 4, 3, 3, 4, 4, 3, right? It's a, yeah. This is eventually periodic. But remember, you also have other periods. You have all periods. See, this is the beauty of this example, right? This NCERT 9th standard textbook. You don't need those papers, you know. If somebody asks you, show me, can you give me an initial value which has period length 1729? You can give it, right? How will you do it? You'll just write the initial value just like that, right? You'll just say 0 point, whatever, you know. I don't care. You'll write 1729 long digits and then put a bar on top of that, right? I mean, you're going to write 1729 digits, which don't repeat, that pattern, and you'll put a bar on top of that. That's the initial value, which when iterated on the decimal map, will give you 1729 period length. Notice this is the beauty of it, right? Any period length that you ask me, I can give you the answer to that, right? And notice that what's happening here, all periodic orbits, right, are rational numbers, right? But you also have non-periodic orbits. They are the irrational numbers. And by the way, all this is there in the, I figured it out, you see, like for example, 1 by root 2, pi minus 3, all these are irrational numbers. They'll all have decimal expansions which never repeat, And I found that this is already there in the NCERT book actually. I went, this is page number 12 actually. You go to page number 12, they do a pretty good job actually, I don't know, they could have just added one paragraph saying it's chaotic and it's done, Everybody's ready for chaos theory. It clearly says here, see, decimal expansion is terminating, recurring, non-terminating, I mean, rational, irrational, everything is there actually in this. And even page number 13 of the book is even amazing, they're talking about square root of 2 and pi and all that. I mean, this is chaos, right? This is prototypical chaos. Now we'll talk about more things. We'll talk about butterfly effect and all that. Any questions on this? So if somebody wants to learn chaos, you tell them you already know chaos. So it's not that you need to teach them anything new. You just have to tell them that you didn't know it was chaos. That's all, It's all there, right? Okay, so let's go forward. So what are the conditions? So I'm going to list out conditions now. So I'm dealing with maps alone, as I said. I'm not going to deal with any continuous systems. It's only I'm going to just talk about discrete stuff and the two one dimensions, right? Nonlinear equations, then bounded. So condition number 4 is okay with all of you, right? Without reading any of those papers, we're able to see, touch, feel, and taste chaos, right? Because all periodic orbits, yes, you're able to see that, right? Whatever periodic orbit you want, you have it in the decimal map, right? So that's fine. That dense, what do you mean by dense? It's a very simple definition. What it says is that you take any real number in 0 to 1 and give me any arbitrary epsilon, some distance you give me, I can find a periodic orbit which comes epsilon close to that initial real number, That's all it is saying basically. That's easy to do, right? It's nothing but, what is it? It's like the number pi, right? We say it's 22 by 7. I mean, it's not really 22 by 7. It's a rational approximation to pi, right? So this density, the notion of dense is you can do rational approximations to irrational numbers. That's all that dense means, And rational numbers are themselves approximation to themselves, right? The argument here is every number can be, in some sense, effectively represented by periodic orbits because it comes arbitrarily close to it. Give me an epsilon. See, what am I doing here? If you take a number, so let's say you have a real number. You have some real number, dot, right? Now you take an epsilon and you say that some, whatever, 10 to the power minus 10, let's say, And can I come up with a periodic initial value which gives me a periodic orbit which is 10 to the power of minus 10 close to this x naught? Yes, you can. What do you need to do? You just go far enough and then truncate it and put a bar on top of it. That's it, right? I mean, you go far enough in this expansion, truncate it, it becomes a rational number. I mean, it becomes a rational number with zeros there. You can either stop there. I mean, that's also why that's period 1, right? It's eventually periodic with period 1, or you put a bar on top of it. It becomes periodic, and you ensure that you go far enough so that the new number, right? The new number. I'm calling the new number as x naught cap, right? This is x naught cap, the truncated one. That's closer to x naught by 10 to the power minus 10. You can do that, right? I mean, you can always do that. So this is taken care, right? I hope this is taken care. What's about the next thing? Non-periodic orbits taken care, right? You just don't repeat. That's all. Done. That's also done. Okay, this is important to ask, right? What's the Lyapunov exponent? They don't talk about that in NCERT, but you can actually. NCERT has done all that. They could just add one more page and talk about Lyapunov exponents, It's very, very simple, right? What is Lyapunov exponent? It's just telling you how things diverge. See, notice the Excel sheet example, right? You went from point 2 to the number of atoms in the universe in amazing time, right? In exponential time. That is the important thing about chaos. It's the errors cascade exponentially, not linearly, So what we're saying is that if you are separated by epsilon, so you have x naught and x naught plus epsilon, after n iterations, what will happen is, so your epsilon will grow. In this example, it will grow like this, right? It will be 10 to the power of n times epsilon. Why is that? Because I'm multiplying by 10 every time, right? I'm multiplying by 10 every time. So it's going to be 10 to the power of n into epsilon for any n, right? That's all that's going to be. So what does Lyapunov exponent capture, right? And there's a last condition. I'll talk about this maybe in my next talk because this is also very important, topological transitivity. I'll talk about it. So I'll just come back to that. So just to complete this whole thing, right? See, 1, 2, 3 is anyway required. 4, 5, and 7, right? 4, 5, and 7 are what is called as Devaney chaos. I mean, Robert Devaney and I don't know, mathematician. So it's called Devaney chaos. And number 6 is called whatever, the Lyapunov. There's some name for it. I forget now. The Lyapunov definition of chaos or something like that. I mean, they're all equivalent. So 4, 5, 7 will imply 6, but there can be. See, the problem with chaos is there will always be some examples which are counter examples. There will always be something which will not follow one of them and things like that. So you have to be very careful. But in most cases, 4, 5, 7 is enough. 4, 5, and 7 is enough. That's the Devaney's definition of chaos. I didn't explain what topological transitivity is, but hopefully we'll come back to that. But I want to just talk about Lyapunov exponent a little bit more, and we'll sort of go forward on that, right? So this, you all know this equation. It's a very, very simple equation, right? What it's saying is, you notice this map, right? What's the map doing? You notice that it's stretching it, right? You're going from 0 to 1 in an interval of 0.1 duration, right? So basically, you're taking any interval you take or any point you take, any interval you take, it gets stretched out, right? It gets stretched out, right? So the question, and that stretching is what is creating this exponential divergence, So the question we're asking is, temporally speaking, because this is a time thing, right? X1, X2, Xn. So we're asking at every point, what is the stretch factor? What is the stretch factor? That is nothing but the first derivative of the function, right? I mean, that's very easy to see, right? And in the case of the decimal map, it's just a constant number. It's 10 basically, 10x, right? It's just 10. And then we're doing it across time now. So we're taking a time average. So we're saying at every point, x1, x2, x3, x4, x5, what is stretching factor? The stretching factor. And that's what we're doing here, right? We're taking the absolute value because we don't care about the sign. We just want the stretching factor. And why we're doing ln? Because we want to extract the exponent here, right? I mean, I can write this as e to the power of, I can write it like this, right? I can write this 10 to the power of n, right? Oh, sorry. Yeah. I can write it like this, no? Oh, sorry. Is it fine? Yeah. Yeah, n will come here, right? Yeah, because yeah, I can write it like this, right? So, and this is your lambda, right? This is your stretch factor, right? So what we're doing is we're taking a time average, but this is where ergodicity comes in. Are you guys familiar with the notion of ergodicity? It's a very simple concept. What the concept says is, for certain systems, it's possible to replace a time average by a space average and vice versa, right? For example, it's about mixing. Let's say that you're cooking rice in a bowl, and if it's a well-mixed thing, you don't have to check every rice whether it's cooked or not, right? You can just take any rice and it's cooked, because it's a well-mixed system, right? You don't have to check every rice and check it, right? You're just sampling it, right? So same thing is true here. You can either, so this here, what you're saying is, look, I'm taking a temporal average here, right? X1 for X1. But if it's ergodic, then, I could actually equally look at the map, and then look at where and all, look at the stretching at every point in the map and take the average of that. That will be spatial average. I could do either time or space. This turns out to be ergodic. But proving something is ergodic would require a little bit, it's not really that much of an work. You have to find the invariant distribution, and then, there are conditions for ergodicity. We can find that. But yeah, this is the well-known Lyapunov exponent, right? And in this case, it turns out to be log 10, right? Yeah. Any questions so far? It's very simple, right? It is so simple that you'll be surprised, right? That, you just have to go back to 9th standard mathematics, basically, Now, what about logistic map and all that? Now you understand this. Now you just have to translate these concepts there, that's all. Right? You have an initial value, you have a trajectory, you have periodic orbits, dense periodic orbits, the notion of dense and all that. Then, okay, let me quickly also talk about, we have time, right? So let me talk about topological transitivity then, right? So let's do that also. So what does topological transitivity say, right? It's a very simple notion. It's a very important idea though. Okay, what it says is, this is the map, right? Now take any two intervals. Let's say I take a small interval here, a small set here, and a small set here. Okay, topological transitivity says that if it's chaotic, rather to be chaotic, the condition required is that if I take these two sets, there is an initial value which, when iterated a finite number of times, will visit the other interval, other set. So I have two sets A and B, wherever on that line 0 to 1. If I am able to guarantee that in a finite number of iterations, I start from one of them and reach the other guy, then it is transitive. That's the condition of topological transitivity. So you can prove this now for the decimal map. Again, you don't need to, you can prove it in your head only. How do you prove it? See, so for example, let's say one of them is here, right? And one of them is here, let's say, right? So what is it? This one here, if it's inside this guy, what will be the what will be the initial value looking like? This is 0.1 to 0.2, right? So it will be 0.1 something. It will be 0.1 something, right? If it's going to be here. And if I wanted to come here, it's 0.7 to 0.8, right? I need to visit 0.7. That means that I need to just put a 7 in the symbolic sequence somewhere, I just need to put 7 somewhere. The moment I put 7 in the thing, it's a shift map, remember, it's a shift map. So 7 will come at the leading digit. So I will visit that. I just need to put 1 and 7. Give me the two intervals, the numbers, and I'm going to just plonk them there and I'm done. So transitivity is, I can prove it by existence, right? I can show you the transitivity actually. So give me any two intervals, I can construct the, see the good thing about this example is that all the proofs are by construction, If you read all these papers, they're generic and they're proving it for a general maps, right? So they become very difficult. They're existence theorems, right? They're talking about existence of periods, period 3 implies all periods. But the good thing about decimal map is I can show you the period. You can touch it, feel it, taste it, so to speak, right? Are you able to see this argument about the transitivity part? Like, you just try to put those numbers in. Give me the two intervals, corresponding symbols, just put them in the decimal expansion. Then I'm guaranteed to visit from that to that, in a finite number of iterations, right? In fact, the good thing is you can go in one iteration, right? Because look at this is a surjective map, right? This is a surjective map. So you're visiting all the intervals in one iteration. If I put 0.17, I'm done, right? Or whatever, if I put 0.17, in one iteration, I go from 1 to 7, I can go 2 iterations, 3 iterations, 4 iterations. I can do all that because because notice here that in this guy here, it's going through all of them, right? So these are very special maps. These are called Markov maps. So I'll talk about it. Yeah, let's go forward. So that's the other condition I want to talk about. So I think we covered, Any questions on this? Because this is the, please, Yes, 4, 5, and 7 implies 6. I think so, yes, because these are the necessary conditions. Sorry, necessary and sufficient conditions. 4, 5, and 7.
Do you have any intuition how 4, 5,
actually, okay. So Devaney talks about this actually. So there is something called, so this sensitivity depends on initial conditions, right? One is Lyapunov exponent, but you can also characterize it by another constant. He calls it some beta or whatever. And he shows that if you have 4, 5, and 7, there will be this constant term, this constant such that the errors will always, I forget now, what's the condition now? So many iterations will cross this. So what he says is that if you have 4, 5, and 7, then you start with some epsilon, you're guaranteed to cross, you're guaranteed to have this exponential divergence or something like that. So there is a equivalence, I forget now, but I think we can go back to the text now. But there's a problem too in the sense that sometimes, there may be some examples where strange examples can be there, where Lyapunov exponent can be 0 or something. I don't know. There can be some special examples. Usually we'll always find this in the chaos community, there'll be something which will violate everything, That you have to be careful, I guess. But my understanding is that 4, 5, and 7 will imply 6, If you have 4, 5, and 7, then you're guaranteed to be have a positive exponent. But finding it may be difficult analytically because you need to find the invariant measure and all that. Empirically, you can probably find it. But numerically, analytically, may be hard to find because you need to find the invariant measure. Without that, you can't find the Lyapunov exponent. Because Lyapunov exponent is an ergodic constant. So you need to know the invariant measure, But that's a good question, yeah. But typically, I know that physicists like just 6, right? In the sense, it's everything. Which is also fine. It's just one number is characterizing the whole thing,
6 to
say that, yeah.
They see 6 and they say chaos.
There's also one more thing called topological entropy. It's an interesting thing. Topological entropy talks about the rate of divergence of trajectory of symbolic sequences. I think something like that. In the symbolic space they define this topological entropy. That's also should be positive. This thing has all of that. This thing, but there's more surprises coming your way. But I'll show you something more interesting which will happen. Any questions on this so far? Because it's all fine. Then we can go forward. Because my talk 2 will build on this, by the way. I'm going to build a network out of these guys, We did this. Similar dynamics we did, right? I don't want to, this talking about, if you have two things, you have binary map. See, I did the decimal map. You can do the binary map. It will be by binary expansions. Ln 2 is the thing. Then you can, this is again nothing very important here. Ternary, you can do everything pretty much, That's the point I wanted to make. Now, what is interesting is that, this one, I just wanted to show you this. It's called the Gauss map. Xn plus 1 is equal to 1 by xn minus 1, integer part of 1 by xn. Unlike the decimal map, unlike the n-ary maps, the intervals here, right? There are infinite number of them. There are infinite number of intervals actually, not a finite number. and they sort of are exponentially becoming smaller and smaller, but there are infinite number of them. So you'll have infinite symbols actually. You'll have infinite symbols. Can you guess what this will be? Because now you know the trick, right? Like all these maps, there is a connection to number theory, right? Because you have decimal expansions, binary expansions, ternary expansions. What will be this kind of an expansion? If you take a initial value here, iterate it out, just record the symbolic sequence, what will I get? Any guesses? Yeah, it's a very interesting thing. You'll get continued fractions. These continued fractions, you'll get them, very interesting, right? So you'll get, so this, and these have, and by the way, it's again a dynamical system, right? So continued fractions also have the same thing. They're periodicity, non-periodic. So all quadratic irrationals will be periodic and things like that, Rationals rationals are also periodic, but it'll terminate to zero. I mean, it'll terminate with a period 1. Quadratic irrationals will be periodic, but of all periods. But other than that, cubic and all, they're all non-periodic. So it's a slightly different cutting the slices, right? We have periodic and non-periodic, right? In the decimal map we had, or the binary, all these maps we had rationals and irrationals. Here it's slightly more nuanced. Here we are saying irrationals with the quadratic irrationals are still periodic, It's slightly different here, So it's very, very interesting again. So yeah, all this again, the invariant measure, all these things have been found. Liopan experiment, all these things have been found for these, Okay, now you can do something more interesting, right? Now you can say, okay, but why should I fix remember my intervals were all of equal dimensions, right? If you look at the decimal map, ternary map, binary map, they all had the same lengths. You can play around with that now. You can say, oh, I don't really care, I can have some smaller, some longer. That's exactly what's happening, right? That's called the generalized Lorentz series, GLS, generalized Lorentz series. It goes all the way back to 1869, 1883, work of Cantor and Lorentz and all that. And notice here that just like the decimal map, the map is surjective, right? Like in the interval, we are mapping to 0 to 1. You have the straight line, 0 to 1. The slopes will all be different, right? The slopes will depend upon the length of this. The slope will depend upon the length of this, right? 1 by P1 to 1 by Pn. This map is amazing because this map has all kinds of properties, Firstly, it is chaotic. Secondly, you might ask, what kind of expansion is it? It's not a binary expansion, not a ternary expansion, not a decimal expansion. It's a generalized expansion, so to speak, It has its own expansion in some sense. So these are like numbers in some generalized basis, What does it mean actually? Look at decimal expansion, right? All symbols have equal weightage, right? Like symbol 7, the digit 7 and digit 8 are the same. I mean, there's no preference. But here it's not like that. Here, some can have larger importance, right? If you go back to the map, right? Some can have larger, some can be larger, some can be smaller, right? Which means that the fraction by which they appear in the expansion can be different, They not be the same, basically. So those kind of things will happen. But what is of interest is, and you can do many things. You can tilt the slopes, you can make it positive, negative. You can play around with all that. And of course, that the tent map, right? The famous tent map, which is continuous but not differentiable, right? It's not differentiable at 0.5. That is very much a GLS, right? And then you have the skew versions and all these guys you have. Okay, now what is amazing is, I don't have time to prove this. The beauty is that there is a nice connection between information theory and the chaos theory here. Now, we talked about Liopan exponent, right? Of all these maps. You can find the Liopan exponent of this map, by the way. It turns out to be this expression here, minus pi log pi. And if you change the base of the log to be the base 2, I mean, you change the base, there's no reason to take base e, You can take base 2 also. Then you'll actually find that this is equal to the Liopan exponent, the Shannon entropy, which is, so what I mean by Shannon entropy is that, so if you think of that entire map I showed, P1 to Pn, right? That can be seen as a Markov chain actually. So by the way, these maps have dual lives, In the daytime, in the morning, they're very well behaved, they're deterministic, they're well behaved. Nighttime, if you don't observe them carefully, they behave stochastically. I mean, in the sense that you can think of them as Markov chains, The same map has these dual characteristics, So the entropy of the Markov chain, right? That is actually captured with the Liopan exponent. So there's a one-to-one correspondence between the two. Otherwise, you have an inequality between them. You don't have an equality, but in this case, it turns out that you can actually, you can, if you're modeling an information source with so many entropy, so many Shannon entropy bits, you can actually see it as a GLS map. You can forget that Markov chain, Markov map thing, and you can see it as a deterministic map, That's the thing, God does not need to play dice, that's what I'm saying. So you can always model stochastic systems of this kind, at least by maps, That's the point I wanted to make. And this equation, right, which is bits per iteration, the way to interpret this, one way to interpret this is, that, remember one thing, right? When I'm looking at the symbolic sequence, right? Yeah, please. Yeah, so the point is, yes, yeah. This thing, right? This thing is deterministic, right? There's nothing random here. There are no coin tosses, no randomness here, right? But what if I said that I don't look at this. Instead, I'll give you a Markov chain. The Markov chain has n states, and the transition probabilities are determined by this P1 to Pn, Okay. So the n states are the n symbols, basically. And the transition, and you have a transition probability matrix for that Markov chain, right? That is determined by this P1 to Pn. So what I'm arguing is that if you just look at measurements, if you just look at the measurements of, if somebody is giving you sequences, right? You cannot tell whether it's from this map or from the chain. It's indistinguishable, That's the point I'm saying. God does not need to play dice. What we're saying is, okay, let's say you're tossing a coin, 0, 1, 0, 1, whatever, right? It could either be a stochastic process or that sequence you're giving me, infinite length sequence, right? I can find the initial condition on the binary map. So God could be just having a binary map, okay? And you give me the infinite measurement or finite, doesn't matter. God will give you the initial value. So both are equivalent. That's what I'm saying, the dual life, So just by measurements, you can never figure out whether our world is, whether universe is deterministic or stochastic in that sense, Of course, then we get into quantum and all that. I mean, I'm just leaving out the quantum stuff for the time being. But just from a classical point of view, you just cannot distinguish between the two, If you're just given coin tosses, it could be from a coin or it could be from a map. That's the way to think of it, It need not be from a, and this also goes back to this story that I've heard. I don't know whether it's true or not, that von Neumann apparently gave, symbols from the logistic map to cryptographers and asked them to figure out whether it's random. And they all said it's random. But of course, it's the logistic map, right? So, and right, all random number generators on the computer, they're all actually non-linear chaotic maps. I mean, they're all non-linear maps which are chaotic actually. You can actually prove it's chaotic also. Because there's no randomness there, right? There's just a mapping between set of, you have a length of your buffer and that determines your x here. Here it's 0 to 1, but there it's whatever. So yeah, I hope that answered your question, right? You can't distinguish between the two, Yeah, so basically, so what is interesting is that these maps can be used for data compression and all. So once we are connecting this to entropy, right? Then what we can do is, given a file, let's say somebody gives you a file, a binary file, zeros and ones, you can find the amount of zeros and ones, and that's your P1 and P2, P1 and 1 minus P1. You can find a GLS corresponding to that, and given that file itself can be encoded as initial condition, initial value, and that can be stored. And we have shown that that's optimal. That's the best storage you can do because you capture the entropy of the file, You can't do better than that. So in other words, there's a nice connection between information theory and data compression and storage and all that with these symbolic sequences. This is a thing. Okay, I think we should stop here. I know I'm completely run out of time. Any more questions? Because I know that I didn't get you to machine learning, but that's okay. What I'll do the forthcoming attraction is what I want to do. Again, see, I'm not a climate person, but I thought at least it'll be a shame if I don't show you some prediction. So we're going to show you some. Hopefully some interesting results on monsoon prediction. I mean, nothing great though. But neurocast learning is what we do. I've set the ground now. We take this GLS maps and we build a network out of it and we build an alternate to deep learning. So I'm going to show you a way of doing classification, which in some ways is better than deep learning. I mean, it has its pros and cons. It's a completely different way of, in that sense. And it could also be done it could also be turned into reservoir. That's also something we'll talk about, that we have a reservoir computing variation of what we have done. So we call it as neurocast learning, and we also use stochastic resonance. The method uses noise for learning, So all this is forthcoming attraction, but this is the last talk actually. So you'll have to, hopefully you're not fatigued by then. Then we will talk about that. Yeah. If you have any questions, or we'll break for lunch, I guess, or we can take 1 or 2 questions, or okay, we can just take 1 or 2 questions and then we can, please, yeah, sure, maybe 2 questions, yeah.
What you just mentioned about make the sequence of numbers.
Yes.
Tell the difference whether it was consistent.
You cannot.
But I was the impression that if I then log xn plus 1 versus xn.
No, there it's fine. There it's not random, right? I mean, the argument there, the one dimension example I gave, but I'm saying in general, if somebody gives you a sequence of measurements, right, you cannot be sure whether it's from a stochastic source or from a map. You cannot tell by measurements alone. Because any set of measurements, finite or infinite, could always come from a map. Even infinite also, that's the point. That's the beauty of these things, right? So because God can know a way of producing that. With the initial value can be given, the map can be given. There's no randomness whatsoever, That's what I meant. But the logistic map case, yes, there, if you just plot it, you know that it's not from a random source, There, that will not work there, yeah. Maybe one more question and then we can stop. Okay, I guess we'll maybe talk over lunch, maybe, yeah. Okay, so I did much lesser than what I expected, but that's fine. So maybe the next one, I'll do a bit of machine learning and then we'll get into the neurocast learning part. Okay, yeah, thank you. Yeah.